The next speaker is Aleksander Kubica from Caltech, and he will be telling us about local decoders for Toric and color codes.
Thank you, David, for the introduction.
Mike.
Thank you for. Does this work? Can you hear me well? The mic is on. You can hear me?
It's on, but it's...
Can you hear me now?
Oh.
I need some help. Sure, thank you. Can you hear me now? Is it okay or not?
Yeah.
Okay. Yeah, thanks for the introduction. And at the beginning, I would like to thank organizers for managing this great conference. Today, I'd like to talk to you about local decoders for Toric and color codes. And this is a joint work with Nicolas Delfos and John Preskill. And this is my last week at Caltech. I'm moving to Waterloo. So in this talk, I will be talking about topological quantum codes, which are very exciting. We can think of those codes as having physical qubits placed on some manifold, for instance, on a surface of a two-dimensional torus. And those codes have local generators. We just need to access small local, geometrically local patches of physical qubits. And information is encoded in non-local degrees of freedom. We can think of logical operators as non-contractible loops or non-contractible sheets if we're in higher dimensions. As we have seen already in this conference, there are two well-known models of topological quantum codes, the Toric code and the color code. And many groups are trying to build small patches of the Toric code, in particular John Martinez's group. Topological quantum codes have many desired properties. They have many fault-tolerant logical gates. What we need to be able to implement is only local measurements. They also have efficient decoders and high thresholds. And in the talk, I will focus my attention on efficient decoders and high thresholds. And it is important to study thresholds, as we have seen in Barbara's talk. And also, it is very important to have fast, efficient decoders, as we've seen in Austin's talk. Unfortunately, there is a price we pay. Geometric locality comes with a price. And there are certain no-go theorems, for instance, Ravi-Koenig, which tell us that only certain logical gates are possible in the dimensions. And as a side remark, topological quantum codes are very exciting to study because they can give us insight into challenging problems from condensed matter physics, for instance. So people have been working on decoders for a long time, and there are many different decoders for the Toric code, not so many for the color code. And some of the decoders are non-local, but we can establish analytical lower bounds on the threshold. Some of them are local, but heuristic. So what I will do in this talk, I will explain to you how to have a local decoder with a provable threshold. And in order to do that, I will start with a generalization of Thun's rule to any lattice. And then I will introduce a local Toric code decoder and show that it has a non-zero threshold. And using this local Toric code decoder, I will explain how to decode the color code by reducing the problem of decoding color code to the problem of decoding the Toric code. And in the last part of the talk, I will shift gears and mention how we achieve three-dimensional color code thresholds from statistical mechanics. And this is a joint work with Michael Beveland, Fernando Brandão, John Preskill, and Chris Tasfori. So we need error correction to prevent errors from accumulation and destroying our information. So if we use an error correction code, there is a notion of a threshold which tells us what's the maximum error rate a code can tolerate. So let's consider a simple case. Let's consider classical memory, which we use to protect one bit. So my bits are plus minus ones. I encoded 1 in an array of ones. What can happen is error can affect my bits. They can be flipped. So what I can do is I can basically look at all the bits and check which is more, 1 or minus 1. But in order to implement such a decoder, I would need to have access to the entire system, to the global information. And this takes time. And if you have more sophisticated algorithms, if you're not able to update or correct errors locally, there might be more errors accumulating in the time needed to figure out what to do. And so it can eventually lead to a problem. So what we're trying to do is we're trying to locally suppress errors. And an attempt to do that is basically Thum's rule. So Thum's rule is specified for spins sitting on the square lattice. Each spin can be plus or minus 1. And the rule is a local rule which tells us that every spin sitting on this face, what we check is our neighbors from the north and from the east. And if we differ from both of them, then we will set ourselves to their common value. So I check, I differ from those two guys, so I restore myself to be 1. Okay, so we get a complication when we think about quantum information. The difficulty is very fundamental. When we want to preserve quantum information, we cannot just look at it. So what we can do is we can use quantum error correcting codes, in particular stabilizer codes. We measure appropriate stabilizers. In the rest of the talk, I will be treating X and Z error correction separately. I can do that because I'm thinking about CSS codes. And also in the talk, I will consider ideal measurements. So what the decoding problem is basically finding error correction from violated stabilizers. I will be using interchangeably violated stabilizers and excitations. So let's see an example. We've seen the Toric code. We know what it is. We have qubits on edges. Stabilizers are Z faces and X vertices. So let's focus our attention to Z errors. Let's assume that this pattern of Z errors happened. Those two X vertices will be violated. Those are my excitations. So now I want to, so by looking at those excitations, I want to make a guess what error happened. So if my guess differs from, if my guess, which is a dark blue, differs from the actual error by some stabilizer, in this case it's two shaded faces, then my error correction is successful. However, if I made such a guess, this dark blue operator, I end up introducing a logical operator and my error correction is unsuccessful. I introduce a logical operator. So as we have already seen, we can consider Toric code or color code beyond 2 dimensions. In general, in the dimensions, it can have excitations which are not point-like. So let's look at an example of the 3D Toric code, which Dan talked about yesterday. Let's consider the Toric code on the cubic lattice, place qubits on faces. Then we will have X-type stabilizers identified with edges, and they basically check nearby qubits. Also Z-type stabilizers on cubes, and they check nearby qubits. So if a Z error happens on this face, neighboring edges of the X-type stabilizer will be violated. So our excitation is a loop-like excitation. So how does the Thum's rule come into play? Well, we can reformulate Thum's rule as a rule for moving domain walls. And how do we see that? Initially, I explained that Thum's rule tells us what to do with spins. If they differ, then I will flip this guy. So when those guys differ, there is a domain wall between them. So what I can pictorially show here is if the Toombs rule tells me that if I see northeast corner on my face, I will decide to flip this corresponding spin to move the domain wall to the dashed blue position. And this can be straightforwardly generalized on the cubic lattice, for instance, or the hypercubic lattice. So I can use it to decode the Toric code. However, there are certain problems with this generalization because this works for the cubic lattice, say. So if we wanted to decode Dan's Toric code on a lattice which is far from being cubic, we would need a rule a la Toom which works on that lattice. In particular, if we were to decode color codes, we would need, they are not defined on the cubic lattices. So how do we do that? Such a generalization is not that trivial. And if we consider just a simple rule, like the one which I told you about, the Toombs rule, move northeast corner, for instance, for this 2D lattice, this rule won't work. So let's see why. I have two loops in this lattice. For each placket, I want to move its northeast corner to be southwest corner. So when I apply my local rule everywhere in the lattice, this face will flip. Now those two faces will flip. But this configuration is persistent. It stays there, and no matter how long I apply my very simple move northeast corner rule, it won't be removed. And things get even worse if I were to consider a lattice built of triangles or tetrahedra. It's not obvious that such a rule can be generalized. In the rest of the talk, I will be particularly interested in deterministic rules because they tend to be simpler to analyze. And since any reasonable tessellation can be split into triangles or simplices, I will focus on triangulated lattices. So the questions which we need to answer and will answer in this talk are, can we have Toombs rule on any lattice? And if we had such a rule, would that work if we use it as a decoder? The first thing which I will describe in the talk is the sweep rule, which is a generalization of Toombs rule, which can work in any dimension for k-dimensional domain walls. And then I will show that a local decoder of the Toric code can be straightforwardly implemented using this sweep rule, and it has non-zero threshold. And then by reducing the problem of color code decoding to Toric code decoding, I will show how to use the sweep rule decoder. So what is the sweep rule? So far we've talked about a rule from the perspective of a face. I'm a face, I look at my neighbors, if they differ, or if there's a corner, if there's a domain wall, I will move the domain wall. So the insight is very simple. Here, we just change the perspective. We're not faces anymore, but now we're vertices. And an ingredient which I need for the sweep rule is I need to introduce the sweep direction. A notion induced by the sweep direction is a notion of an extremal vertex. And I say that a vertex is extremal if local restriction to the domain wall is in the sweep direction from V. So what it means is that this vertex is extremal because the domain wall is in the sweep direction, but those two are not extremal. So now we're ready to state the sweep rule. So for every vertex, what I do is, if this vertex is extremal, I will flip spins on faces in the sweep direction so that the domain wall is pushed. So in this configuration, this vertex is extremal. So if I were to flip those two faces, I will move my domain wall in the sweep direction. And this sweep rule can be defined beyond 2 dimensions in a similar way. But in higher dimensions, there is a subtlety how to flip right cells. Now we're ready to talk about properties of the sweep rule. So we need the sweep direction, and this direction induces a partial order on the set of vertices in the lattice. So an alternative way of thinking of it is we can think of this sweep direction, which I denote T for time, as space-time. And now there's some causal relation between vertices in the lattice. So in particular, I will have paths in my lattice. A path is just a set of edges, but I can have also a causal path. So for instance, those 2 points are connected by a causal path because this path always goes in the increasing direction of t. 2 notions which I need in order to prove that this rule has a threshold are a notion of a cone. So a cone is defined for a vertex v, and it's basically its past light cone. It's the set of all vertices which can be reached if I go along the causal path in the opposite direction to time. And a supremum, so let's say that S is a set of vertices, a subset of vertices. Then I define supremum of the set of vertices as the least lower bound on those vertices. So for this set of vertices S, the supremum would be this vertex V. So first property of the rule is its correction region. So if I start with some domain wall, this rule guarantees that if I keep applying it, the domain wall will stay within the cone of the supremum of the domain wall. So basically what I do is, for each domain wall, I find its supremum, and then I look at its cone, and the domain wall is guaranteed to stay in this region. And the other property needed to show that there's threshold is that there's a monotone for this rule. So basically, if I consider my domain wall, I find its supremum, then I consider all possible causal paths between the between the supremum and any point of the domain wall. So for instance, this dashed blue line is a causal path. And what the rule guarantees is that if I keep applying to the domain wall, this monotone decreases every time I apply the local rule. So let's see the rule in action. So this is the extremal vertex. This is also an extremal vertex. So in the first time step, those guys change. Then what are the extremal vertices? Here, here, and here. So it flips here. Now the extremal vertex is only here, and the domain wall is being pushed all the way to the supremum, and it disappears. So how can we define the sweep decoder? We consider toric codes in 3 or more dimensions, which have excitations at least 1-dimensional. And now the sweep decoder is defined as follows. We simultaneously apply the local rule at each and every vertex for n times. And after n times, we declare that flipped spins are our correction. So this decoder can fail for 2 reasons, for 2 different reasons. First of all, some big domain walls might not be removed in n time steps. And the second reason why this decoder fails is that the correction might be faulty. We might introduce a logical error. So what we will show is that the sweep decoder has non-zero threshold, and by that I mean that if the error rate, the physical error rate, is below a certain value, then the probability of successful error correction goes to 1 in the limit of infinite system size. So I need 2 key lemmas. On this slide, I will borrow ideas from Gach, Harrington, Bravi, and Ha. So let's consider our system. Red dots denote errors. And what I need to do is I need to introduce a notion of a level n chunk. Level n chunk is 2 disjoint level n minus 1 chunks, such that they sit within a ball of a certain diameter. So in particular, in this picture, level 0 chunks would be single errors everywhere. Level 1 chunks would be nearby pairs of errors. Level 2 chunks will be 2 pairs of errors which are nearby, and so on and so forth. So the first lemma is that if we consider sufficiently small physical error, then the probability of having level n error chunk is suppressed doubly exponentially in n. Okay, so intuitively we should think of it as don't worry about high-level chunks. Another notion which is needed is level n error. So level n errors is defined as a union of all level n chunks. Level n error is contained in level n-1 error. This leads to a disjoint decomposition of errors. Basically, we can write the error happening in the system as level 0 errors, which are not level 1 errors, plus level 1 errors, which are not level 2 errors, and so on and so forth. And the second lemma which we need for the proof is that if we consider now a Qi connected component of errors of the ith level, which are not I plus 1 level, then we are guaranteed that the diameter of this error scales at most as Q to the I, and the distance between this connected component and the rest of errors of level I is lower bounded by Q to the I plus 1 over 3. So pictorially, basically this level 1 error is guaranteed to be far from other level 1 errors or higher, but it is not necessarily guaranteed to be far from level 0 errors. So how to put those things together? In order to prove that there's a threshold for the Toric code or the color code, we need certain assumptions about the lattice. So we, in particular, need the fact that the lattice is locally Euclidean, and different paths in different directions are comparable. So what we have seen on the previous slide is that Qi-connected components have a diameter which is at most Q to the I. But we also had the property of the sweep rule, which is the monotone. So at each time step, we push, or rather we shrink our domain wall by 1. So what we can argue is that in time proportional to Q to the I, we can remove those Qi connected components. So in particular, if we have an isolated error, it will be removed in one time step. If we have level 1 error, which is not 2, it will be removed in time proportional to Q, and so on. Also, because those connected components are of the level I are far from other errors of a higher level, errors from higher level do not interfere with those errors when we remove them. And the last piece which we need is that when we correct low-level errors, because we are guaranteed that their error correction sits within a cone which is small, and thus it's a correctable region, we are guaranteed that when we apply this error correction, there's no logical error introduced. So so the last thing is that basically we run our local update rule for the time which is proportional to Q to the power of m, where m is of the order of log L. And when we run the local rule for such a time, higher level errors might not be removed. But as I was arguing, they are highly unlikely, so we would basically ignore them. And thus, the failure of the decoder will be solely due to high-level errors. And we can upper bound that. The failure of the decoder would be some polynomial function of the lattice size and an exponential function in L. And this goes to 0 as the code size goes to infinity. So now let me briefly tell you how to reduce the color code decoding to the Toric code decoding. We've seen the color code, but so that we're on the same page, let me briefly tell you how it's defined. We need to consider a lattice which is 3 colorable and 3 valent. We would place qubits on vertices, and for every phase, we will have X phase and Z phase stabilizers. Okay, so color codes are exciting because they have logical Clifford gates, which are transversal. In higher dimensions, we can go outside the Clifford hierarchy. Also, color codes are very closely related to the Toric code, so this can give us insights about non-Clifford gates with the Toric code in higher dimensions, for instance. But the problem with color codes is, or at least it seems to be a problem, that decoding of them is more challenging. And why is that? Well, if some error happens on a qubit, then in the case of the Toric code, we would create a pair of excitations. In case of the color code, we would create a triple of excitations. And now the problem of pairing it up when we have branching points becomes difficult. So now I would like to tell you a bit about decoding of color codes. So in order to do that, I need to switch to the dual lattice. So I can say that color codes are defined on triangulated lattices, or in higher dimensions on simplicial lattices. Qubits will be placed on triangles. Stabilizers in 2 dimensions will be identified with vertices, and they would have support on neighboring qubits. So for instance, this is the valid color code lattice. Now I don't color faces. I'm in the dual lattice, so I color vertices. 2 neighboring vertices have to be colored into different colors. So as I was saying on the previous slide, the color and Toric code are related. So first idea would be, maybe we can map the color code to the Toric code setting and use existing Toric code decoders to decode the color code. Unfortunately, life is not that simple. And in particular, what gets difficult is that even if we have uncorrelated errors in the Toric code, in the color code, sorry, when we map it to the Toric code setting, there will be certain correlations. So what Nicolas proposed a couple of years ago is that we can decode 2D Toric code by projection. So those shaded triangles, not that visible, are errors. So if those errors happen in my color code, syndromes which will be violated are those black circles. So my syndromes, the information I use, the syndrome, is 0-dimensional. The error, or the error correction I want to find, is 2-dimensional. So how do we get from 0 to 2 dimensions? We don't go directly. Rather, we go through 1 dimension. And how to do that? From 0-dimensional syndromes, we will use Toric code decoders to go to 1 dimension. And then from 1 dimension, by some global lifting, we will get to 2 dimensions. So how does the decoder work? Let me show you an animation. I need to consider 3 sublattices. So first sublattice I consider is red-green sublattice. I can think of this sublattice as basically the decoding of the Toric code problem. I need to pair up excitations along those edges in this sublattice. So that's what I do. I do it for other 2 colors of sublattices. For instance, this green-blue. So what I end up with is a collection of loops. Some of them might not be contractible. But in this case, I was lucky. I got contractible loops. So, so I got from 0 dimensions to 1 dimensions. Now the last step is I need to fill those loops. So I fill them up. And what I can see here is that over here and over there, errors were removed totally. Over here, this was my error. This is my error correction. So I ended up implementing this operator. But it's a stabilizer, so it's good. So correction succeeded. So right. So far, there have been no local decoders for color code. And an open problem was what to do with decoding in higher dimensions. So just for the sake of concreteness, let me focus on 3D color code, which with dual lattice. Qubits are on tetrahedra. Stabilizers will be on vertices and edges. So the neighborhood of every vertex looks like that. A naive approach, a naive generalization of Delphos's decoder would be use Toric code decoder and sequentially lift So since my syndromes are 0 and 1 dimensional, I can sequentially first decode it with the Toric code from 0 to 1 and from 1 to 2, and then sequentially lift from 2 to 3 and from 1 to 2 first, and then from 2 to 3. But those lifting procedures are non-local, and the analysis of the decoder and threshold becomes very difficult. So what we actually propose is that you can do a decoder with a local projection. The projection is always local, but also a local lifting in the dimensions. What is cool about this approach is that we can use any Toric code decoder we want, and the color code decoder will be fully local if the Toric code decoder is fully local. So in particular, in 3 dimensions for loop-like excitations, we have fully local decoder. And also, the Toric code thresholds allow us to lower bound color code thresholds. So let me show you some preliminary numerics. Let's look at the 3D Toric and color codes on the BCC lattice, which I showed earlier, with 0-point-like excitations. So if I consider this Toric code, this color code on BCC lattice, projected lattices where the Toric code is supported would be the cubic lattice. We get some threshold of close to 3%, and half BCC lattice where we get threshold of 5.8%. When we do analysis for the color code on the BCC lattice, we get a threshold of 0.76%. And the bound we get from the threshold of the Toric code on the threshold on the color code is basically 0.75. So we see that within our precision, those two, our threshold estimate and the lower bound match. So in the remaining 10 minutes of the talk, I would like to very briefly tell you about the 3-dimensional color code thresholds from statistical mechanics. What we've discussed is analytic thresholds and some numerics, and in general, those analytical lower bounds are very far off from actual values of thresholds. So in order to get a better grasp on those values, we do need to do some numerics. So what was introduced in a seminal paper by Dennis et al. Is that we can reduce the problem of optimal decoding. We can reduce the problem of finding the optimal threshold for the Toric code to an analysis which can be done within statistical mechanical realm. In particular, if we analyze a classical spin model, the random bond Ising model, we can find out what the threshold is. So this random bond Ising model is a classical spin model, 2 body interactions. Some couplings are +1, some couplings are -1. This model has 2 parameters, the disorder strength, which tells us what the fraction of antiferromagnetic bonds is, and the temperature at which the model is held. And what was shown by Dennis et al. Is that as long as there's a mapping between the decoding problem and the statistical mechanical problem along the Nishimori line. And as long as we're in the order phase, we can successfully correct. If we go beyond, we will fail. So when we find the intersection of this blue line with the phase boundary, we can figure out what the threshold is. And this mapping is cool because it can let us to import all the machinery from statistical mechanics to a quantum information problem. So what we do in this work is basically we introduce 2 new statistical mechanical models which are relevant for 3-dimensional color codes. And we investigate their phase diagrams. And from their phase diagrams, we can figure out what the thresholds are. So as I already said, we analyze the color code from the dual lattice perspective. We consider the code on the BCC lattice, qubits are on tetrahedra. There would be 2 types of stabilizers identified with vertices and edges. Logical operators in this 3-dimensional color code can be thought of as 1-dimensional string-like operators and 2-dimensional sheet-like operators. Because those 2 operators are of different dimensionality, we end up with 2 different spin models, which we need to separately independently analyze. Those 2 spin models are 4-body spin model, Basically, what this model is constructed by placing spins on vertices and including 4 body terms in my Hamiltonian for every tetrahedron. The other model is obtained by placing spins on edges and taking 6 body terms to be in my Hamiltonian. So in our numerical approach, what we've done is we implemented Monte Carlo simulation. Since the energy landscape of those models is fairly rough, and we want to be able to explore the configuration space efficiently, we implemented a parallel tempering technique. But now there are a couple of questions: how to choose temperatures for parallel tempering, a question when the system thermalize, and also one has to be careful and take into account symmetries of the model. For detecting the phase transition, we look at specific heat, spin-spin correlation, and Wilson loop. And also, one has to be careful about finite size scaling effects. So let me just show you very briefly the numerics. We look at specific heat, correlation length, and scaling of Wilson loop. And from those data, we can infer the phase diagrams for the 4-body random coupling IC model. Each point on the boundary was found by keeping the disorder fixed and sweeping temperatures. Basically, we were finding where the critical temperature is, where the phase transition happens. That's how we found this point and every other point on this diagram. And this gives us a threshold of close to 28% for a sheet-like logical operator. For the 6-body random coupling IC model, we did the same trick. We found all those boundary points, and we arrived at the threshold of close to 2%, and this is a threshold valid for string-like logical operators. So to conclude, in the first part of the talk, I was talking about local decoders for Toric and color codes with probable threshold. And as we've seen in the previous talks, it is very important to have efficient decoders. And you cannot make a decoder faster than a local decoder. And it is also very assuring if you can show that there's a threshold. You have a lower analytical bound on the threshold. And the other part of the talk, I told you about thresholds of the 3D color code from statistical mechanical mapping. And let me make just one comment about 3D subsystem codes. So when you think of threshold for error correction for those guys, this number is relevant for this model because we should think of one of these string-like logical operators. And as an ongoing work, we've been thinking about incorporating measurement errors into the analysis. And with that, I would like to thank you for your attention.
Thank you, Alec. Let's take some questions.
How does your actual decoder performance for the 3D color code compares with these thresholds? Do you have data?
Right. So let's see. The number I got was 0.75 for point-like excitations, and the upper bound was 1.9%. And for the loop-like excitations in the Toric code, the upper bound on the cubic lattice is 23%, and we observe something close to 16%.
Are there any other questions? All right, well, if there are no other questions, let's thank Alec again.